Right now, somewhere in the constellation Cygnus, roughly 6,070 light-years from Earth, there is a point in space where reality simply stops making sense. It is called Cygnus X1. It is a black hole approximately 21 times the mass of our Sun, and it is pulling gas from a nearby blue supergiant star at velocities exceeding 400 kilometers per second. That gas spirals inward, forming a disk of superheated plasma reaching temperatures of 20 million degrees Kelvin. At the center of that disk is a boundary, not a wall, not a surface, a boundary in the geometry of space-time itself, a sphere roughly 124 kilometers across from which nothing, not light, not information, not even the concept of outward, can escape. You are about to cross that boundary, not metaphorically, not as a thought experiment you can safely observe from a distance. You, in your body, falling feet first, are going to descend into a black hole. And what will happen to you on the way down will shatter everything you think you understand about space, time, light, gravity, and the nature of reality itself. The journey will begin gently, almost peacefully. It will end in a place where the known laws of physics collapse into paradox, where density becomes infinite and time ceases to have meaning. Between those two extremes lies the most extraordinary sequence of events the universe can offer to any traveler. This is the story of that fall. Every distance, every velocity, every temperature, and every distortion of time described here is grounded in the mathematics of general relativity, Albert Einstein's 1915 masterwork that remains, after more than a century, our most precise description of how gravity shapes the cosmos. The equations have been tested to extraordinary precision. They have predicted gravitational waves detected by LIGO. They have predicted the exact shape of the black hole shadow photographed by the Event Horizon Telescope in 2019. They are among the most thoroughly verified predictions in all of science, and they describe your fall with breathtaking, terrifying specificity. If this journey expands the way you see the universe, even slightly, a like and a subscribe genuinely helps this channel continue. It is a small thing, but it makes an enormous difference. Thank you. Are you ready? Let's begin. Imagine you are aboard a spacecraft. It is the most advanced vessel humanity has ever constructed. Let us not concern ourselves with how you got here or what propulsion brought you to this place. What matters is where you are. You are holding position at a distance of 10,000 kilometers from the event horizon of a stellar mass black hole. The black hole has a mass of 10 solar masses, which means it contains the gravitational equivalent of 10 of our suns compressed into a sphere with a Schwarzschild radius of approximately 29.5 kilometers. That is the radius of the event horizon, the point of no return. The entire mass of 10 suns occupies a region of space smaller than a mid-sized city. From this distance of 10,000 kilometers, the black hole does not look like what you might expect. There is no swirling vortex of purple energy. There is no menacing dark sphere hovering in space with dramatic lightning crackling around its edges. What you see when you look toward it is a region of absolute blackness surrounded by the strangest optical phenomena you have ever witnessed. Stars that should be behind the black hole are visible around its edges, their light bent by gravity into arcs and rings. Some stars appear duplicated. You can see the same star on both sides of the black hole simultaneously, because light from that star has taken two different curved paths around the gravitational well to reach your eyes. Other stars appear smeared into elongated streaks, their images stretched by the differential bending of light rays passing at slightly different distances from the center. The entire background of stars appears to ripple and shift as though you are looking at the universe through a lens made of curved space-time. And at the center of all this distortion sits a perfect circle of nothing. Not dark matter, not a dark surface, nothing. The absence of all light, all information, all signal, a hole in the visible universe. This effect, the bending of light by gravity, is called gravitational lensing, and it was one of the earliest predictions of general relativity to be experimentally confirmed. In 1919, during a total solar eclipse, British astronomer Arthur Eddington measured the positions of stars appearing near the edge of the sun and found that their apparent positions had shifted by approximately 1.75 arcseconds, exactly the amount predicted by Einstein's equations. The sun, with its relatively modest mass, bends light by a tiny amount. A black hole, with space-time curvature millions of times more extreme, bends light so severely that photons can orbit the black hole in complete circles. This happens at a distance of 1.5 Schwarzschild radii from the center, a sphere called the photon sphere. At this distance, light does not escape and does not fall in. It orbits, tracing a circular path around the black hole, trapped in an unstable equilibrium. A slight perturbation inward, and the photon spirals into the event horizon. A slight perturbation outward, and it escapes to infinity. This is what physicists call the black hole's shadow, and it is larger than the event horizon itself. The shadow extends to roughly 2.6 times the Schwarzschild radius, about 77 kilometers across for this particular black hole, because light passing near the event horizon is captured even if it was not aimed directly at the center. Photons that pass within 1.5 Schwarzschild radii of the center are doomed. They spiral inward and never escape. This means the darkness you see is not just the event horizon. It is the entire region from which light cannot reach you. A sphere of gravitational capture larger than the point of no return itself. The photon sphere has another consequence that is worth pausing over, because it reveals something deeply counterintuitive about the geometry of space near a black hole. If you were orbiting at the photon sphere, which you cannot do stably, but imagine it for a moment, and you looked straight ahead, you would see the back of your own head. Light, leaving the back of your skull, would travel all the way around the black hole and return to your eyes. In fact, you would see multiple images of yourself because light can orbit the black hole 2, 3, or infinitely many times before reaching your eyes. Each successive image would be dimmer and more distorted, a fading hall of mirrors effect produced by the curvature of space-time itself. Around the edge of this shadow, if matter is falling into the black hole, you would see something extraordinary. Superheated gas forms an accretion disk, a swirling, flattened ring of material orbiting at tremendous velocities. The innermost stable circular orbit around a non-rotating black hole sits at 3 Schwarzschild radii, roughly 88.5 kilometers from the center. This is the closest distance at which matter can maintain a stable orbit. Inside this orbit, there are no stable paths. Material that crosses this boundary spirals rapidly and inevitably inward toward the event horizon. Material at the innermost stable orbit moves at approximately half the speed of light, 150,000 kilometers per second. At these velocities, the gas is heated by friction and compression to tens of millions of degrees, radiating intensely in X-rays. Stellar mass black holes with active accretion disks are among the brightest X-ray sources in the galaxy. Cygnus X1, the first black hole ever identified by astronomers, was discovered precisely because of this X-ray emission, detected by an Aerobee-sounding rocket in 1964. The identification of Cygnus X1 as a black hole was not immediate. It took nearly a decade of observations and theoretical arguments. The X-ray source was found to be orbiting a blue supergiant star designated HDE 226868, and the dynamics of the binary system indicated that the unseen companion had a mass too large to be a neutron star, the only other compact object that could explain the X-ray emission. In 1974, Stephen Hawking famously made a bet with Kip Thorne that Cygnus X1 was not a black hole. It was a playful wager. Hawking described it as an insurance policy, noting that if black holes did not exist, he would at least have the consolation of winning the bet. He conceded the bet in 1990, when the evidence had become overwhelming. But the accretion disk does not look like a flat ring when you observe it from nearby. Because of the extreme curvature of space-time, light from the far side of the disk is bent up and over the black hole, creating the illusion that the disk wraps around the black hole from all sides. You can see the top of the disk above the shadow and the bottom of the disk below it simultaneously, because light from both sides has been gravitationally lensed into your line of sight. If you have seen the depiction of the black hole gargantua in the film Interstellar, that image was generated using the actual equations of general relativity by physicist Kip Thorne and visual effects artist Paul Franklin. The rendering required solving the geodesic equations, the equations that describe the paths of light rays through curved space-time, for tens of millions of individual light rays, tracing each one from the camera backward through the warped geometry to determine what it would show. The computation generated enough data for 2 scientific papers published in the journal Classical and Quantum Gravity. The real thing would look even stranger than the movie depicted, because in a real scenario, relativistic Doppler effects would make one side of the disk dramatically brighter than the other. The side rotating toward you would be blue-shifted and intensified, photons piling up, their frequencies pushed higher, their energies increased. The side rotating away would be red-shifted and dimmed. Photons stretched, their frequencies lowered, their energies reduced. The accretion disk would appear lopsided, one half blazing with fierce blue-white brilliance, the other a dull, fading red. The filmmakers deliberately reduced this effect in Interstellar because test audiences found the asymmetric appearance confusing. Reality, as it often does, proved too strange for fiction. You take all of this in from your position at 10,000 kilometers. Your instruments confirm that time is already behaving unusually. At this distance from a 10 solar mass black hole, the gravitational time dilation factor is small but measurable. Your clock is running approximately 0.15% slower than an identical clock far from the black hole. For every 1,000 seconds that pass on your clock, 1,001.5 seconds pass for an observer far away. This is not a metaphor. This is not an illusion caused by signal delay or mechanical imprecision. Time itself, the actual rate at which physical processes unfold, is slower for you than for someone watching from a safe distance. Your atoms vibrate more slowly. Your neurons fire more slowly. Your thoughts unfold more slowly. Chemical reactions in your body proceed at a rate fractionally less than they would in flat, empty space. Light reaching you from distant stars is slightly blue-shifted because it has fallen into a deeper gravitational well to reach your eyes, gaining energy as it descends. You do not feel any of this. From your perspective, everything seems perfectly normal. Your heartbeat sounds the same. Your breathing feels unchanged. Your watch ticks at what seems like its usual rate. It is only when you compare your clock to a distant one, by exchanging light signals, for example, that the discrepancy reveals itself. This is not a new or speculative effect. Gravitational time dilation was first measured experimentally in 1959 by Robert Pound and Glenn Rebka at Harvard University. They placed a gamma-ray emitter in the basement of the Jefferson Tower and a detector at the top, 22.5 meters higher. The gamma rays climbing upward against Earth's gravity lost a tiny amount of energy, a frequency shift of just 2.46 parts in a million billion. This shift was exactly the amount predicted by general relativity. Clocks at the top of a building tick faster than clocks at the bottom. The GPS satellites orbiting 20,200 kilometers above Earth run their atomic clocks about 45 microseconds per day, faster than identical clocks on the ground. And if this difference were not corrected for, GPS positions would drift by roughly 10 kilometers per day. These are real, measurable, consequential effects of gravitational time dilation, the same physics that, near a black hole, is amplified to universe-altering extremes. This is the first lesson of falling into a black hole. The experience of the one who falls and the experience of the one who watches are fundamentally, irreconcilably different. This divergence will grow more extreme with every kilometer you descend. By the end of your journey, you and your distant observer will disagree not just on how much time has passed, but on whether certain events have occurred at all. You have studied the physics, you have reviewed the mathematics, and now, floating at 10,000 kilometers from the event horizon, you do something that no force in the universe can undo. You leave the spacecraft, you turn off your engines, and you fall. The first thing you notice is that nothing seems to happen. You are in free fall, which means you are weightless. Just as an astronaut aboard the International Space Station is weightless, not because gravity is absent. At the station's altitude of roughly 400 kilometers, Earth's gravitational acceleration is still about 90% of its surface value. But because everything around them is falling at the same rate, the astronaut, the station, the air inside the station, and the water droplets floating in the cabin are all accelerating toward Earth's center at the same rate, and so they experience no relative force between them. They float. Free fall is the absence of felt gravity, even in the presence of enormous gravitational acceleration. You and every atom of your body are accelerating toward the black hole at exactly the same rate, and so you feel no force at all. This is a deep and remarkable feature of gravity that Einstein recognized as the key insight leading to general relativity. He called it the equivalence principle, the observation that free fall is locally indistinguishable from floating in empty space, far from any gravitational source. In his own words, Einstein described the moment of this realization as the happiest thought of my life. He was working at the patent office in Bern in 1907, and he imagined a man falling from the roof of a building. During the fall, the man would feel weightless. He would not feel gravity. Locally, in his immediate vicinity, the effects of gravity would be completely absent. Einstein realized that this meant gravity was not a force in the traditional sense. It was something else entirely, a feature of the geometry of space-time that produces the illusion of force when you resist it, by standing on the ground, for example, but vanishes when you surrender to it, in free fall. If you closed your eyes right now, falling toward the most extreme gravitational object in the universe, you would have no way of knowing you were falling at all. You would feel serene, weightless, free. You could perform any local experiment, measure the speed of light, test the laws of electromagnetism, mix chemicals, observe nuclear decay, and every result would be identical to what you would measure in empty space, far from any gravitational influence. This is the equivalence principle in action, and it is not approximate. It is exact to every precision we have ever been able to test. But you are not free. You are accelerating. At 10,000 kilometers from the event horizon, the gravitational acceleration is approximately 44,300 meters per second squared, about 4,500 times the gravitational acceleration at Earth's surface. You do not feel this acceleration because you are in free fall, but its consequences are real and mounting. Your velocity is increasing with every passing second. The black hole is pulling you harder and harder, and while you experience weightlessness, your speed relative to the distant universe is climbing rapidly. Within minutes of leaving the spacecraft, you are traveling at thousands of kilometers per second. The journey from 10,000 kilometers to the event horizon will take, on your clock, a matter of tens of minutes, and you will not feel any of it. The silence, the weightlessness, the peaceful drift, all of it is a profound deception orchestrated by the equivalence principle. You are in the grip of the most powerful gravitational field any stellar object can produce, and it feels like floating in a calm sea. At 5,000 kilometers from the event horizon, you are halfway to the point of no return in terms of distance, though not in terms of time. The journey accelerates as you descend, so the second half takes far less time than the first. Your velocity is now enormous, a growing fraction of the speed of light. The gravitational time dilation has increased noticeably. Your clock is running about 0.3% slower than the distant observer's clock. Still a small number, still imperceptible to you, but the trend is clear and the mathematics is unforgiving. The deeper you fall, the slower your time flows relative to the outside universe. Something else is beginning to happen, though at this distance it is still subtle. The black hole's gravity is not uniform. It is stronger at your feet than at your head, because your feet are closer to the center of mass. This difference in gravitational pull across the length of your body is called a tidal force, and it is the same phenomenon that causes ocean tides on Earth. The moon pulls slightly harder on the near side of the Earth than on the far side, and this differential creates a stretching effect. The moon's tidal force on Earth is remarkably gentle. It raises the ocean surface by about half a meter, but the physics is identical in kind, if not in magnitude, to what you are about to experience. Near a black hole, this stretching becomes extreme. At 5,000 kilometers from the event horizon of a 10 solar mass black hole, the tidal force across a 2-meter-tall human body is still manageable. Noticeable to sensitive instruments, but not yet painful. You might feel a faint sensation of being gently pulled along your vertical axis, as though some invisible force were trying to make you slightly taller. Simultaneously, a very faint compression pushes inward on your sides because the gravitational field lines converge toward the center, gently squeezing you laterally. This combination, stretching vertically and compressing horizontally, is the beginning of what physicists have informally named spaghettification. The word was coined by Stephen Hawking in his 1988 bestseller, A Brief History of Time. It sounds almost comical. The phenomenon it describes is profoundly violent. It will not remain gentle. At 1,000 kilometers from the event horizon, the tidal forces have grown substantially. The difference in gravitational acceleration between your feet and your head is now significant enough to be felt as a persistent pull, not just on instruments, but in your body. Your feet are being dragged downward with more force than your head. Your spine is being stretched. Your internal organs are experiencing slightly different gravitational pulls depending on their position in your body. Simultaneously, the lateral compressive force is squeezing your torso inward. Your shoulders are being pushed closer together. Your rib cage is under gentle but increasing pressure. Every atom of your body is subject to a slightly different gravitational acceleration than its neighbors, and these differences are growing with every kilometer you fall. To understand why the tidal forces escalate so rapidly, consider the mathematics. The tidal acceleration across a body of length L at a distance r from a mass m is given by the equation. Tidal acceleration equals 2 gml divided by r cubed. The critical feature of this equation is the r-cubed term in the denominator. As r decreases, as you fall closer to the center, tidal forces increase as the inverse cube of the distance. This is an extremely steep relationship. Halving your distance from the center increases tidal forces by a factor of 8. Reducing your distance by a factor of 10 increases tidal forces by a factor of 1,000. This means that the escalation from barely noticeable to lethal spans a surprisingly small range of distance. The transition from comfort to catastrophe is not gradual. It is sudden, steep, and merciless. At 500 kilometers from the event horizon, the tidal forces have become intensely uncomfortable. The stretching along your body is now a persistent, powerful pull, as though invisible hands are gripping your feet and your head and pulling in opposite directions with hundreds of pounds of force. The lateral compression is squeezing your torso visibly narrower. If you could look down at your body, you would see that you are being deformed, elongated and thinned. Your blood is redistributing under the tidal gradient, pooling toward your extremities as the differential pull draws fluid away from your center. Your spine is under significant tension. Your bones, which are strong but not infinitely so, are approaching their structural limits. You are still conscious, still aware, but you are in considerable and growing discomfort, and it is getting worse with every passing second. Meanwhile, the view has become almost hallucinatory. As you fall deeper into the gravitational well, the light from the universe above you is being gravitationally blue-shifted, pushed to higher frequencies and higher energies. Stars that appeared white from a distance now glow faintly blue. Stars that were faintly red have shifted into the visible spectrum and become newly visible. Distant galaxies that were invisible to the naked eye, their light normally confined to the infrared spectrum, have been blue-shifted into the visible range. The X-ray sources in the sky are being shifted to gamma-ray frequencies. Looking up, away from the black hole, you see the entire observable universe compressed into a shrinking circle of increasingly intense light directly above you. This effect, called gravitational aberration, is a consequence of your increasing velocity. As you fall faster, the angle at which incoming light can reach your eyes narrows, concentrating all incoming photons into a tighter and tighter cone centered on the direction directly away from the black hole. The sky above you is brilliant, compressed, and surreal, a kaleidoscopic bullseye of blue-shifted, aberrated starlight. The sky around and below you is absolute darkness. You are falling into a tunnel of nothing, with the entire luminous universe gathered into a shrinking, bright ring above your head. At 100 kilometers from the event horizon, just 70.5 kilometers from the center, the tidal forces are approaching the limits of what the human body can withstand. The force difference between your head and your feet is now thousands of newtons. Your body is being stretched with a force equivalent to hundreds of kilograms pulling at each end. Bones are creaking under the strain. Connective tissue is reaching its tensile limits. The lateral compression has narrowed your torso substantially. Every joint in your body is under tension. Your circulatory system is struggling to function as blood is pulled toward your feet and head simultaneously, draining from your core. You are, quite literally, beginning the process of spaghettification in earnest. For a 10 solar mass black hole, the tidal forces become lethal to a human at a distance of roughly 320 kilometers from the center, approximately 290 kilometers from the event horizon. This is well outside the event horizon. You will be killed by tidal forces before you even reach the point of no return. For this particular black hole, spaghettification is your fate long before the event horizon becomes relevant to your physical experience. The event horizon is almost an afterthought. A mathematical boundary you cross is a stream of disassociated atoms, long past any capacity for conscious experience. But there is an extraordinary caveat, and it changes everything. The size of the event horizon scales linearly with mass. Double the mass, double the Schwarzschild radius. A 20 solar mass black hole has an event horizon with a radius of 59 kilometers. A 100 solar mass black hole, 295 kilometers. A million solar masses, 2.95 million kilometers. The relationship is perfectly proportional, a straight line on a graph. But tidal forces at the event horizon do not follow this same scaling. Tidal forces at the horizon scale inversely with the square of the mass. Double the mass, and tidal forces at the horizon decrease by a factor of 4. Increase the mass by a factor of 10, and tidal forces at the horizon decrease by a factor of 100. Increase the mass by a factor of 1,000,000, and tidal forces at the horizon decrease by a factor of 1,000,000,000,000. This is one of the most counterintuitive results in all of black hole physics, and it deserves a moment of careful thought. Your intuition says that a bigger black hole should be more dangerous, more mass, more gravity, more destruction. And in a sense, that is true. A more massive black hole has a stronger gravitational field at any given distance from its center. But the event horizon is not at a fixed distance from the center. It grows with mass, and it grows linearly, while the tidal force at any fixed distance grows only as the mass itself. The net result is that the event horizon of a more massive black hole is, in a very real sense, gentler than the event horizon of a less massive one. The tidal forces that would kill you occur deeper inside the black hole, farther from the horizon, giving you more time and more space to survive after crossing. Consider the supermassive black hole at the center of the Milky Way galaxy, Sagittarius A star. Its mass is approximately 4 million solar masses. Its Schwarzschild radius is about 12 million kilometers, roughly 17 times the radius of the Sun, or about 8% of the distance from Earth to the Sun. The event horizon of Sagittarius A star is a sphere larger than Mercury's orbit around the Sun. And at that event horizon, the tidal force across a 2-meter human body is approximately 0.05 meters per second squared. That is 1/200th of the gravitational acceleration at Earth's surface. You would not feel it. You would not notice it. No instrument on your body would register anything unusual. You could cross the event horizon of Sagittarius A star in perfect comfort, reading a book, sipping coffee, having a conversation, and the most dramatic boundary in the universe would pass you by in silence. Now consider the ultramassive black holes, the titans that sit at the centers of the largest galaxies in the observable universe. The galaxy NGC 4889, a giant elliptical galaxy in the Coma cluster roughly 300 million light-years from Earth, harbors a black hole with an estimated mass of 21 billion solar masses. Its event horizon would be roughly 62 billion kilometers across, larger than the orbit of Pluto by a wide margin, extending far beyond the heliopause that marks the boundary of our solar system. TON 618, a hyperluminous quasar, roughly 10.4 billion light-years away, is powered by a black hole with an estimated mass of 66 billion solar masses. Its Schwarzschild radius is approximately 197 billion kilometers. Light takes more than 18 hours to cross its event horizon. The tidal forces at its event horizon are so vanishingly small that they would be unmeasurable by any instrument humans have ever constructed. The gravitational gradient across a human body at that horizon is smaller than the tidal force you experience from the moon while sitting in your living room. You could cross the event horizon of TON 618 while eating dinner, conducting a conversation, and performing delicate surgery, and nothing, absolutely nothing, would indicate that you had just passed the point of no return. There would be no sign, no signal, no alarm, no tremor. The laws of physics, as measured in your immediate vicinity, would be indistinguishable from those anywhere else in the universe. You would have crossed the most absolute boundary in the known cosmos, and you would not know it. This is perhaps the most counterintuitive truth about black holes. The most dangerous boundary in the universe is, for sufficiently large black holes, completely imperceptible. There is no wall. There is no membrane. There is no flash of light or tremor of force. The event horizon is a mathematical surface defined purely by the geometry of space-time. It is the set of points from which light-speed signals can no longer reach the outside universe. It is defined not by anything happening at that location, but by the global structure of space-time, by the behavior of light rays in the distant future. Crossing it feels like nothing, because locally, nothing happens. The horror of the event horizon is not what it does to you. It is what it has done to the geometry of the universe around you, and that change is invisible from the inside, and yet you have crossed it, and nothing you can ever do, no engine you can fire, no signal you can send, no speed you can achieve will reverse it. So let us restart your journey. Let us place you not near a 10 solar mass stellar black hole that would tear you apart before you reached its horizon, but in the vicinity of a supermassive black hole, one massive enough that you can survive the crossing of the event horizon and experience the interior of a black hole while still conscious, still intact, still capable of witnessing what happens inside a region of space from which no information can escape. Let us say the black hole has a mass of 10 million solar masses, roughly 2.5 times the mass of Sagittarius A star. Its Schwarzschild radius is approximately 29.5 million kilometers, about 20% of the distance from the Earth to the Sun. The event horizon is a sphere with a diameter of 59 million kilometers. Tidal forces at the event horizon are comfortable. You will survive the crossing. You will be conscious for what comes after. You begin your fall from a great distance. The experience is, initially, identical to what was described before. Weightlessness, silence, the gradually intensifying optical distortions of gravitational lensing. But this time, the journey takes much longer. The distances are vastly larger. You fall for hours, watching the black hole's shadow grow slowly in your field of view, watching the lensed stars dance and shimmer around its perfectly dark edge. And throughout that long, quiet descent, time dilation builds. Here is where the experience becomes genuinely alien. As you approach the event horizon of this supermassive black hole, time dilation is accelerating toward its extreme. Let us trace it step by step, because the numbers tell a story that words alone cannot convey. At a distance of 100 Schwarzschild radii from the center, about 2.95 billion kilometers, roughly the distance from the Sun to Uranus, time dilation is modest. Your clock runs about 0.5% slow relative to a distant observer. This is the time dilation equivalent of living on a neutron star, noticeable to precision instruments, imperceptible to human senses. At 10 Schwarzschild radii, 295 million kilometers from the center, about twice the distance from the Earth to the Sun, your clock runs about 5% slow. An hour on your watch corresponds to roughly 63 minutes in the outside universe. You are beginning to drift out of temporal sync with the cosmos. If you were exchanging messages with a friend far from the black hole, you would notice that their messages seem to arrive slightly too quickly, as though they were speaking at a slightly accelerated pace. Your friend, in turn, would notice that your messages were arriving slightly too slowly, your voice dragging just perceptibly. At 3 Schwarzschild radii, 88.5 million kilometers from the center, time dilation reaches approximately 18%. You are now orbiting at the innermost stable circular orbit, the closest distance at which stable orbits exist. Material in the accretion disk at this radius is traveling at roughly half the speed of light. Time here is running at 82% of its rate in the distant universe. An hour for you is 73 minutes out there. The drift is becoming significant. An afternoon on your clock would cost your distant friend a full working day. At 2 Schwarzschild radii, 59 million kilometers from the center, or 29.5 million kilometers above the horizon, your clock is running about 29% slower than the distant observers. For every 10 seconds on your watch, 14 seconds pass outside. The universe around you is beginning to speed up. If you could somehow receive a television broadcast from Earth, ignoring the obvious distances involved, you would see people moving noticeably faster, as though the playback speed had been increased by a third. Time on Earth is accelerating relative to your frame, not because anything has changed on Earth, but because your time has slowed. At 1.5 Schwarzschild radii, you are now at the photon sphere. This is where light itself orbits the black hole. The time dilation here is approximately 42%. Your clock runs at 58% of the rate of a distant clock. Nearly half of your time has been squeezed away by gravity. An hour for you is nearly 2 hours for the outside universe. The Earth broadcast would now look like a nature documentary played at nearly double speed, people scurrying, traffic zipping, clouds racing. At 1.1 Schwarzschild radii, roughly 3 million kilometers above the event horizon, time dilation has reached approximately 70%. Your clock is running at less than 1/3 the rate of the outside universe. If you could somehow watch that broadcast from Earth, you would see it playing at triple speed or more. People would be scurrying about like insects in a time lapse. Days would flash by in hours. Seasons would change in what felt like weeks. The longer you linger near the horizon, the more of Earth's future flickers past you. At 1.01 Schwarzschild radii, just 295,000 kilometers above the horizon, roughly the distance from the Earth to the Moon, time dilation exceeds 90%. Your clock is running at 1/10 the rate of the distant universe. 10 seconds for you equals 100 seconds outside. An hour for you equals more than 10 hours out there. A day of hovering here would cost the outside universe 10 days. At 1.001 Schwarzschild radii, 29,500 kilometers above the horizon, time dilation is at 97%. Your seconds are stretched to more than 30 seconds outside. You could wait a single day and find that nearly a month had passed on Earth. You could wait a year and find that more than 30 years had elapsed. A generation, born and grown, while you experienced 12 months. At 1.0001 Schwarzschild radii, 2,950 kilometers above the horizon, time dilation exceeds 99%. Your clock is running at less than 1% of the rate of the distant universe. 1 minute for you is more than an hour and a half outside. 1 day for you is nearly a year out there. 1 year for you would see a century pass on Earth. This is gravitational time dilation carried to its logical extreme, and it is one of the most remarkable predictions of general relativity. Time is not a constant. It is not a fixed background against which events play out. It is not the steady ticking of some cosmic metronome, indifferent to the contents of the universe. Time is a flexible, deformable dimension of space-time, warped by mass and energy just as space is warped. Near a massive object, time runs slower. Near a black hole, time nearly stops. At the event horizon, for an outside observer, it stops entirely. The time dilation factor diverges to infinity. Your clock, as seen from outside, takes an infinite amount of external time to tick its final tick before the crossing. This has a profound implication for what the outside universe sees when it watches you fall. As you approach the event horizon, the light signals you send back become increasingly red-shifted. Photons climbing out of the gravitational well lose energy, and losing energy means their wavelengths stretch, their frequencies drop. Visible light shifts to infrared. Infrared shifts to microwave. Microwave shifts to radio. Each photon you emit takes longer to climb out of the gravitational well and arrives at the distant observer carrying less and less energy. Your image dims. Your radio signals fade. Your clock, as observed from outside, slows and approaches zero. The outside universe sees you freeze at the horizon's edge. Your image grows dimmer and redder, stretched and faded. The last photons you emitted before crossing are red-shifted to wavelengths so long that they become undetectable, lost in the cosmic microwave background, stretched beyond the capability of any telescope to distinguish from noise. After a finite time, typically on the order of milliseconds to seconds for a distant observer watching at relevant wavelengths, you become completely undetectable. Not because you have crossed the horizon, but because the photons carrying information about you have been red-shifted to oblivion. In a very real sense, the outside universe loses you, not by watching you cross a boundary, but by watching you dissolve into it. You become part of the horizon. Your information, your mass, your energy, all of it is absorbed into the black hole's gravitational field. From outside, you are gone. Your story, as far as the external universe is concerned, has ended. From inside, you are still falling, but you are not hovering. You are falling. And as you approach the event horizon in freefall, something subtle but crucial happens. From your perspective, you cross the horizon in finite time. Your watch ticks normally. You feel nothing special at the moment of crossing. The laws of physics, as measured locally, do not change. There is no sign, no flash, no barrier. One moment you are outside the event horizon, the next moment you are inside it. You may not even be able to identify the exact instant of crossing because there is nothing local to mark it. The event horizon is a global property of the space-time geometry, not a local phenomenon. It is defined by the future behavior of light rays, not by anything happening at the horizon itself. You cannot detect the horizon by any local experiment. No measurement you perform, no matter how sensitive, no matter how clever, can tell you the moment you cross from outside to inside. Both descriptions, the outside observer seeing you freeze and fade and you sailing smoothly through, are correct. They are descriptions of the same events from two different frames of reference, and general relativity insists that both are equally valid. There is no privileged frame. There is no real answer to the question of whether you have crossed the event horizon. It depends entirely on who is asking and where they are standing when they ask. This is one of the deepest and most unsettling features of general relativity. Reality is not observer-independent in the way our intuition demands. What happens, what actually, physically occurs, depends on the reference frame of the observer. This is not a limitation of measurement or technology or human perception. It is a fundamental property of space-time itself. You have crossed the event horizon. You are inside the black hole. And now, the very fabric of reality around you has undergone a transformation so profound that it challenges the limits of human language to describe. The first thing to understand about the interior of a black hole is that the roles of space and time have exchanged. This is not a metaphor. It is not a poetic interpretation. It is a precise mathematical statement about the structure of space-time inside the Schwarzschild radius. Outside the event horizon, the radial coordinate, the distance from the center, is a spatial dimension. You can move toward the center or away from it. You have freedom of radial movement, just as you have freedom to move left or right, forward or backward. The radial direction is a degree of freedom, a dimension in which you can choose your direction. But inside the event horizon, the mathematics of general relativity reveals something extraordinary. The radial coordinate becomes time-like, and the time coordinate becomes space-like. The roles have switched. Moving toward the center is no longer a choice you make in space. It is a progression in time. The singularity is not a place at the center of the black hole that you are falling toward in space. It is a moment in the future of the black hole that you are falling toward in time. It is in your future as surely and as inescapably as tomorrow. Consider what this means. You cannot avoid moving toward the singularity any more than you can avoid moving forward in time. You cannot turn around, because turning around in the radial direction would be equivalent to traveling backward in time, which is forbidden by the causal structure of space-time. Every path you can take, every direction you can move, leads toward the singularity. It is not that the gravitational pull is too strong for you to resist. It is that the very geometry of space-time has been so severely warped that all future directed paths converge on a single point. The singularity is not a place you are being pulled toward. It is a moment you are being carried toward by the passage of time itself. This is why nothing can escape a black hole. It is not that the gravitational pull is too strong for light to overcome, as though light were a ball thrown upward that falls back down. The reality is stranger and more absolute. Inside the event horizon, every direction in space points toward the singularity. There is no outward direction. The concept of away from the center has ceased to exist as a spatial direction you can point in. All future directed paths, including the path of light itself, the fastest thing in the universe, lead to the singularity. Escape is not impossible because of insufficient force. Escape is impossible because the geometry of space-time has been warped so severely that outward is no longer a direction that exists. Let this settle for a moment. You are inside a region of space where every direction leads to the center. Forward, backward, left, right, up, down. All of these directions, in terms of the radial coordinate, point inward. The singularity is everywhere in your future. The event horizon is everywhere in your past. You are trapped not by force, but by geometry. Not by a wall, but by the shape of time itself. And yet, locally, everything still seems normal. You are in free fall. You are weightless. The laws of physics, as measured in your immediate vicinity, are the same as they would be anywhere else in the universe. You can still shine a flashlight, and the light travels at the speed of light. You can still drop a ball, and it floats beside you in free fall. You can still send a radio signal, and it propagates at 299,792 kilometers per second. The equivalence principle still holds. General relativity guarantees that locally, in a sufficiently small region of space-time, the effects of gravity are indistinguishable from the absence of gravity. It is only when you look at the large-scale structure of space-time that the horror of your situation becomes apparent. Locally, you are free. Globally, you are doomed. How much time do you have inside the black hole before you reach the singularity? This depends on the mass of the black hole and your trajectory. For a Schwarzschild black hole, the maximum proper time, the time measured on your own clock, between crossing the event horizon and reaching the singularity is given by a simple and elegant formula. It equals pi times the gravitational radius divided by the speed of light, equivalently pi times g times m divided by c cubed. For our 10 million solar mass black hole, this works out to approximately 87 seconds. 87 seconds, 1 minute, and 27 seconds. That is the maximum time you can experience inside this black hole. From the moment you cross the event horizon to the moment you reach the singularity, you have at most a minute and a half of proper time. This is the maximum, achieved if you fall freely and do not attempt to accelerate. Counterintuitively, if you fire your rockets in an attempt to slow your descent, you actually reduce the time you have remaining. This violates every intuition from everyday life, where braking always gives you more time before reaching a destination. But inside the black hole, the situation is fundamentally different. The singularity is not a place in space you are approaching. It is a moment in time you are approaching. Accelerating changes your trajectory through space-time in a way that, inside the horizon, shortcuts to that moment. The geometry is analogous to the twin paradox in special relativity, where the twin who accelerates and decelerates ages less than the twin who travels in a straight line through space-time. Inside the black hole, the straight line, freefall, maximizes your remaining time. Any deviation from freefall, any engine thrust, any attempt to resist, reduces it. The best strategy, the one that maximizes your remaining time, is to do nothing. Simply fall. Surrender to the geometry. Accept the trajectory that space-time has chosen for you. There is a lesson in that, perhaps, though it is not one most of us would choose to learn this way. For larger black holes, the interior time increases proportionally with mass. For Sagittarius A star, at 4 million solar masses, the maximum interior time is about 35 seconds. For a billion solar mass black hole, roughly 2.4 hours. For TON 618, at 66 billion solar masses, the maximum interior time would be approximately 9.6 hours. Nearly 10 hours of consciousness inside a region of space-time from which no information can escape. 10 hours in a place that, according to external observers, you never entered. 10 hours of experience, of thought, of awareness, sealed behind a horizon that the rest of the universe will never penetrate. Let us stay with our 10 million solar mass black hole. You have crossed the event horizon. You have 87 seconds. What do you see? Looking outward, back toward the event horizon you have just crossed, you see something remarkable. The universe you have left behind has not vanished. Light from outside is still falling into the black hole, crossing the event horizon, and reaching your eyes. You can still see stars. You can still see galaxies. You can still see the accretion disk glowing around you. The event horizon is not a physical barrier that blocks light. It is a one-way boundary. Light can cross it inward, but not outward. So light from the outside universe continues to stream in, and you can still receive it. But the view is deeply strange. The outside universe appears compressed into a shrinking, circular window directly behind you, directly in the direction of the event horizon you have just crossed. This window is ringed with the distorted, gravitationally lensed images of every star and galaxy that is still sending light into the black hole. As you fall deeper, this window shrinks because the angle at which incoming light can reach your eyes narrows. The universe is collapsing into a point of light above your head, a luminous iris closing against the darkness. There is a common misconception that if you looked outward from inside a black hole, you would see the entire future history of the universe flash before your eyes. Every star dying, every galaxy colliding, the heat death of the cosmos playing out in seconds as time dilation compresses infinite external time into your finite remaining moments. This is incorrect, and it is worth understanding why. While time dilation is extreme near the event horizon, you cross the horizon in finite, proper time. You do not linger at the horizon, you pass through it, and once inside, you continue to fall for a finite duration, 87 seconds in our case. During those 87 seconds, a finite amount of light from the outside universe crosses the horizon after you and reaches your eyes. The total additional external time you observe is modest, perhaps seconds to minutes beyond the moment of your crossing, depending on your trajectory and the geometry of the infalling light. You do not see the end of the universe. You see the universe continuing normally, just compressed and distorted. The entire future of the universe scenario applies only to the mathematically idealized and physically impossible case of hovering at the event horizon for an infinite amount of time. Essentially, using an infinitely powerful engine to hold position at the exact mathematical surface of the horizon. This is not physically realizable. No engine can hold position at the event horizon because the thrust required diverges to infinity. And in any case, you are not hovering. You are falling. Looking inward, toward the singularity, you see nothing. Absolute nothing. No light is coming from that direction because nothing has preceded you down this particular trajectory that could send light back toward you. The interior of the black hole ahead of you is dark, silent, and empty, save for the warped geometry of space-time itself, drawing you inexorably forward in time toward the singularity. As your 87 seconds tick away, tidal forces are reasserting themselves. Even for this supermassive black hole, whose tidal forces at the event horizon were negligible, the forces grow as you approach the singularity. The tidal acceleration still scales as the inverse cube of the distance from the center, and the center is now getting close. The gentle stretching that was imperceptible at the horizon becomes noticeable, then uncomfortable, then painful. The compression from the sides begins. You are being elongated and narrowed. In the final seconds, the tidal forces escalate beyond anything the human body can withstand. The force differential between your head and your feet exceeds the tensile strength of bone, then of steel, then of carbon nanotubes, then of any material known to physics. Your body is torn apart, not by an explosion, not by heat, not by impact, but by the simple, cold geometry of curved space-time pulling different parts of you towards slightly different destinations at vastly different rates. First, you are stretched into a thin column. Then that column is stretched further and narrowed. Then the atoms that once formed your body are pulled into a thread, then a filament, then a stream of subatomic particles elongated beyond recognition. The tidal forces continue to increase without limit. Atomic nuclei are torn apart. Protons and neutrons are separated. Quarks are stripped from their bonds. The fundamental structure of matter itself is shredded by a force that is, at its root, nothing more than the geometry of space and time. There is no heat, no radiation, no chemical reaction. Just the differential curvature of space-time, pulling things apart because different points in space are accelerating at different rates toward a center that is not a place but a moment. And then you reach the singularity, or rather, the singularity reaches you. It is not a place in space, it is a moment in time, the final moment of your time inside the black hole. And at that moment, according to general relativity, the curvature of space-time becomes infinite. Density becomes infinite. Tidal forces become infinite. The volume of space you occupy is compressed to zero. Every known quantity that describes the physics of your situation, temperature, pressure, density, gravitational field strength, diverges to infinity. This is what physicists call a singularity, and it represents not a physical object, but a breakdown, a failure, a confession, a point where the equations of general relativity produce infinite values, which is mathematics' way of saying the theory can no longer describe what is happening. The map has reached the edge of the known world, and beyond it, there are only dragons. The singularity is general relativity's admission of its own limits. When a physical theory produces infinities, it is almost always a signal that the theory is incomplete, that some crucial piece of physics is missing, some deeper framework waiting to be discovered that will replace the infinity with a finite, meaningful answer. This has happened before in physics. In the early 20th century, classical electromagnetism predicted that a charged particle, like an electron, should have infinite self-energy. The energy of its own electric field diverges as you approach the point-like particle. This infinity was eventually resolved by quantum electrodynamics, which replaced the point-like classical electron with a quantum mechanical object, whose interactions at very short distances are modified by quantum effects. The infinity was a signal that classical physics was incomplete at small scales, and quantum mechanics provided the missing piece. The singularity at the center of a black hole is believed to be the same kind of signal. General relativity describes gravity as the curvature of space-time by mass and energy. It is a classical theory, meaning it treats space-time as smooth and continuous, infinitely divisible into smaller and smaller regions, like a perfectly smooth rubber sheet that can be bent and stretched, but never torn, never granular, never discrete. But we know from quantum mechanics, the other great pillar of modern physics, that nature is not smooth at the smallest scales. At the Planck length, roughly 1.6 times 10 to the negative 35 meters, the smooth fabric of space-time is expected to give way to something else. What that something else looks like is the central question of quantum gravity. The Planck length is almost inconceivably small. An atom is roughly 10 to the negative 10 meters across. A proton is roughly 10 to the negative 15 meters. The Planck length is 20 orders of magnitude smaller than a proton, 20 factors of 10. If a proton were the size of the observable universe, the Planck length would be about the size of a grain of sand. At this scale, the smooth geometry of general relativity is expected to dissolve into quantum fluctuations. A seething, roiling foam of space-time where the very concepts of distance and duration lose their meaning. A theory of quantum gravity, one that successfully unifies general relativity and quantum mechanics, would presumably resolve the singularity, replacing the infinite density and infinite curvature with some finite, extreme, but physically meaningful description of what happens at the center of a black hole. Several candidate theories are under active development. String theory proposes that the fundamental constituents of nature are not point-like particles, but tiny, vibrating strings of energy, roughly the Planck length in size. In string theory, the singularity might be replaced by a small but finite region of extremely high energy density, where the strings are compressed to their minimum size but never to a mathematical point. The physics of this region would be governed by the full machinery of string theory, which modifies general relativity at very short distances and very high energies. Loop quantum gravity takes a different approach, proposing that space-time itself is quantized, that it comes in discrete, indivisible chunks, like pixels on a screen, rather than being a smooth continuum. In loop quantum gravity, there is a minimum possible volume of space and a minimum possible duration of time. The singularity cannot form because space-time cannot be compressed below its quantum minimum. Instead, the collapsing matter might bounce, creating a new expanding region of space-time, possibly a baby universe, instead of a mathematical point of infinite density. Causal set theory, developed primarily by Raphael Sorkin and collaborators, proposes that space-time is fundamentally a discrete structure, a set of points with causal relationships between them, like a vast network of events connected by light cones. In this framework, the smooth geometry of general relativity is an approximation that emerges at large scales, much as the smooth surface of a lake is an approximation that emerges from the discrete molecules of water. The singularity would be resolved because the discrete structure of space-time prevents the infinite compression that general relativity predicts. None of these theories has been experimentally verified. None has made a testable prediction about black hole interiors that could distinguish it from the others. This is not surprising. The energies and distance scales involved are far beyond the reach of any conceivable experiment. The Large Hadron Collider, the most powerful particle accelerator ever built, probes distances down to about 10 to the negative 19 meters. The Planck scale is 16 orders of magnitude smaller. Reaching it directly would require a particle accelerator roughly the size of the Milky Way galaxy. What this means is that we can describe your journey with extraordinary precision up to a point, the point where tidal forces tear you apart and the curvature of space-time approaches the Planck scale. Beyond that point, we do not know. General relativity says you hit a singularity of infinite density. Quantum mechanics says infinities do not occur in nature. One of them must be wrong, or both are incomplete. The true fate of matter at the center of a black hole remains one of the deepest, unsolved problems in all of physics. But the mysteries of the black hole do not end with the singularity. They extend outward, to the event horizon itself, where another profound puzzle has been growing for half a century. A puzzle that may ultimately reveal the true nature of space-time, information, and reality. In 1974, Stephen Hawking published a paper that would become one of the most influential and disruptive results in the history of theoretical physics. The paper, titled Black Hole Explosions, appeared in the journal Nature and was only 2 pages long. Its consequences have consumed theoretical physics for 50 years and show no signs of resolution. Hawking had been applying the techniques of quantum field theory, the mathematical framework that describes quantum mechanics in the context of special relativity, to the curved space-time near a black hole's event horizon. Quantum field theory describes the vacuum of space not as truly empty, but as a seething soup of quantum fluctuations. Pairs of virtual particles, a particle and its antiparticle, are continuously being created and annihilated throughout all of space. These virtual pairs exist for unimaginably brief durations, borrowing energy from the vacuum in accordance with Heisenberg's uncertainty principle and returning it almost immediately. Near the event horizon of a black hole, Hawking discovered, something extraordinary happens to these virtual particle pairs. A pair that forms very close to the horizon can be separated by the extreme curvature of space-time. One particle falls through the horizon and into the black hole. The other particle escapes to infinity, carrying real energy away from the black hole. For this to satisfy conservation of energy, the infalling particle must carry negative energy, effectively reducing the mass of the black hole. The escaping particle is real, detectable, and carries energy. From a distance, it appears as though the black hole is radiating. The result is that black holes slowly evaporate. They emit a faint glow of thermal radiation with the statistical properties of heat, characterized by a specific temperature. The temperature of a black hole is inversely proportional to its mass. Smaller black holes are hotter. Larger black holes are colder. For a stellar mass black hole of 10 solar masses, the Hawking temperature is approximately 6 nanokelvins, 6 billionths of a degree above absolute zero. This is astonishingly cold, far colder than the 2.725 Kelvin cosmic microwave background radiation that fills the universe. A stellar mass black hole is therefore absorbing far more energy from the CMB than it is emitting through Hawking radiation. It is gaining mass, not losing it. It is growing, not shrinking. Only in the far distant future, when the universe has expanded and cooled to temperatures below the Hawking temperature of the black hole, will the balance reverse. Then, and only then, will the black hole begin to shrink. For a stellar mass black hole, this will not happen for roughly 10 to the 67th power years, a number so large that writing it requires 68 digits. The current age of the universe is 1.38 times 10 to the 10th power years. The evaporation timescale exceeds the current age of the universe by a factor of more than 10 to the 56th power. For supermassive black holes, the timescales are even more extreme. Our 10 million solar mass black hole has a Hawking temperature of roughly 6 times 10 to the negative 15 Kelvin, about 1 million times colder than the stellar mass case. Its evaporation timescale is approximately 2 times 10 to the 87th power years. For TON 618, at 66 billion solar masses, the evaporation time is roughly 10 to the 99th power years. These numbers are so large that they defy comprehension. The protons that make up ordinary matter are predicted, by some theories, to decay after roughly 10 to the 40th power years. The era of stellar evolution, the time during which stars form, shine, and die, will end in roughly 10 to the 14th power years. Black holes will be the last macroscopic objects in the universe, persisting through eons of darkness and cold, slowly, imperceptibly radiating their mass away, one photon at a time. But eventually, in the unimaginably distant future, every black hole will evaporate. As a black hole shrinks, its temperature increases. As its temperature increases, it radiates more energy. As it radiates more energy, it shrinks faster. The process accelerates. In the final fraction of a second, the remaining mass of the black hole is converted entirely into a burst of radiation. The Hawking temperature, which started at nanokelvins, has climbed to trillions of degrees. The black hole, which began as the darkest and coldest object in the universe, ends its life in a flash of light, and then it is gone. Every bit of mass that ever fell into it, every star, every planet, every photon, every atom of your body has been returned to the universe as thermal radiation, spread across eons of cosmic time. And this is where the deepest mystery emerges. The radiation emitted by a black hole through the Hawking process is thermal. It has the spectrum of a perfect black body, a smooth, featureless curve defined entirely by a single number, the temperature. It carries no information about what fell into the black hole. None. A black hole formed from the collapse of a star made of iron emits exactly the same Hawking radiation as a black hole of the same mass formed from a star made of hydrogen, or from a collection of grand pianos, or from 1 trillion copies of the collected works of Shakespeare. The radiation depends only on the mass, charge, and angular momentum of the black hole. The 3 quantities that, according to the no-hair theorem, completely define a black hole's external properties. Everything else, every detail of what went in, every memory of the internal structure of the matter that formed the black hole appears to be permanently erased. This is the black hole information paradox, and it has been called the most important unsolved problem in theoretical physics. It has consumed the careers of some of the greatest minds of the past 50 years. It has generated thousands of papers, dozens of proposed resolutions, and no consensus. The paradox arises from a direct conflict between general relativity and quantum mechanics, the two most fundamental and most thoroughly tested theories in all of physics. Quantum mechanics contains a principle called unitarity. Unitarity states that the quantum mechanical evolution of a system is reversible. If you know the complete quantum state of a system at any one time, you can, in principle, calculate its state at any other time, past or future. Information is never created and never destroyed. It can be scrambled, encoded, redistributed, and hidden, but it can never be eliminated. Unitarity is not an optional feature of quantum mechanics. It is embedded in the mathematical structure of the theory at the deepest level. Violating unitarity would require abandoning the entire framework of quantum mechanics, the Schrödinger equation, the superposition principle, the probabilistic interpretation of measurement, all of it. Every experiment ever performed is consistent with unitarity. Not a single violation has ever been observed, but Hawking's calculation appeared to show that a black hole violates unitarity. Complex, information-rich matter falls in. Featureless, information-free thermal radiation comes out. The information about the original state of the matter appears to be permanently destroyed, not just hidden or scrambled, but genuinely, irretrievably lost. This cannot be right if quantum mechanics is correct, and quantum mechanics has been tested to extraordinary precision. Its predictions have been confirmed to more than 10 decimal places in experiments measuring the magnetic moment of the electron, making it the most precisely verified theory in the history of science. So either quantum mechanics is wrong in the context of extreme gravity, which would be an extraordinary claim requiring extraordinary evidence, or Hawking's calculation is missing something, or our understanding of space-time itself is fundamentally incomplete. Hawking himself initially argued that information was truly destroyed. He believed that black holes represented a genuine exception to the unitarity of quantum mechanics, that the extreme conditions inside a black hole could do what no other physical process in the universe could do: erase information permanently. He made a famous bet with physicist John Preskill of Caltech in 1997, with Kip Thorne siding with Hawking against Preskill. The stakes were an encyclopedia of the winner's choice, a symbol of the information at stake in the debate. In 2004, at a conference in Dublin, Hawking announced that he had changed his mind. He now believed that information was preserved, that it was encoded in the Hawking radiation in subtle correlations, that his original calculation had been too simple to detect. He conceded the bet and presented Preskill with a baseball encyclopedia, a total encyclopedia of baseball information. Thorne did not concede. The debate continued, but Hawking's concession, while influential, did not resolve the paradox. How, specifically, does information escape a black hole? The proposals that have been put forward are among the most radical and far-reaching ideas in modern physics. The holographic principle, developed by Gerard T. Hooft in 1993 and elaborated by Leonard Susskind, proposes that all the information about the three-dimensional interior of a black hole is encoded on its two-dimensional event horizon. Just as a hologram uses a flat surface to store a three-dimensional image, the event horizon stores a complete description of everything inside the black hole. In this picture, the three-dimensional interior is in some sense a projection, an emergent phenomenon arising from the information encoded on the boundary. Nothing is truly lost. The information is scrambled, encoded in the quantum state of the horizon, and eventually released in the correlations of the Hawking radiation over the black hole's immense lifetime. The holographic principle has been given mathematical rigor through the ADS/CFT correspondence, discovered by Juan Maldacena in 1997. This remarkable conjecture, widely regarded as one of the most important theoretical results of the past 30 years, establishes a precise mathematical equivalence between a theory of gravity in a certain type of space-time, anti-de Sitter space, and a quantum field theory without gravity living on the boundary of that space-time. In this framework, the boundary theory is manifestly unitary. Information is preserved by construction. The equivalence then implies that the gravitational theory in the interior must also preserve information, even though this is not obvious from the gravitational perspective. The firewall hypothesis, advanced by Ahmed Almehri, Donald Marolf, Joseph Polchinski, and James Sully in 2012, known as the AMPS group, proposes something far more disturbing. Their argument, based on careful analysis of quantum entanglement near the event horizon, suggests that the event horizon might not be the smooth, featureless boundary that general relativity predicts. Instead, quantum effects might create a curtain of high-energy radiation at the horizon, a firewall that would destroy anything attempting to cross it. This would resolve the information paradox by ensuring that nothing actually enters the black hole interior in the form that classical physics describes, but it does so at an enormous cost. It violates the equivalence principle, the foundational postulate of general relativity. If a firewall exists, then falling through the event horizon is not a smooth, uneventful experience. It is lethal. The two pillars of modern physics, general relativity and quantum mechanics, would be in direct, irreconcilable conflict at the event horizon. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013, takes perhaps the most audacious approach. ER refers to Einstein-Rosen bridges, wormholes connecting distant regions of space-time, first described by Einstein and Nathan Rosen in 1935. EPR refers to the Einstein-Podolsky-Rosen paradox, the phenomenon of quantum entanglement, also described in 1935, in which distant particles share quantum correlations that cannot be explained by any local mechanism. The ER equals EPR conjecture proposes that these two phenomena, wormholes and entanglement, are fundamentally the same thing. Every pair of entangled quantum particles is connected by a microscopic wormhole, and every wormhole is a manifestation of quantum entanglement between the regions it connects. If this is correct, then the information that falls into a black hole is not trapped behind the event horizon. It is connected to the external universe through a web of quantum entanglement that manifests as a network of microscopic wormholes threading through space-time. The interior and exterior of the black hole are not truly separate. They are connected by quantum threads that preserve information even as classical communication is impossible. The black hole's event horizon is not a wall of ignorance but a barrier of complexity. The information is there, encoded in the entanglement structure of the Hawking radiation, but extracting it would require measuring quantum correlations of a complexity that exceeds the computational capacity of any conceivable device. These proposals are not speculation in the pejorative sense. They are mathematically rigorous conjectures, explored using the most powerful tools of theoretical physics, by researchers whose track records include Nobel Prizes, Fields Medal caliber work, and some of the most cited papers in the history of science. But none has been proven. None has been experimentally verified. The black hole information paradox remains open, a wound in the body of theoretical physics that has not healed in 50 years. Its resolution will almost certainly require a revolution in our understanding of the relationship between gravity, quantum mechanics, space, time, and information. Your fall into the black hole, your spaghettification, your encounter with the singularity, was not just a dramatic journey through extreme physics. It was a journey to the frontier of human knowledge. The black hole is the place where our two greatest theories of nature collide, and neither survives the collision intact. The singularity says general relativity is incomplete. The information paradox says quantum mechanics cannot be applied to black holes without contradiction. Somewhere in the gap between these failures lies the next great theory of physics. The theory that will do for the 21st century what general relativity and quantum mechanics did for the 20th. But there is yet another twist in this story, and it concerns the type of black hole you would most likely encounter in the real universe. Everything described so far has assumed a Schwarzschild black hole, a perfectly spherical, non-rotating, electrically neutral black hole. This is the simplest solution to Einstein's field equations, derived by Karl Schwarzschild in December 1915, barely a month after Einstein published the final form of general relativity. And just months before Schwarzschild died of a rare autoimmune disease contracted while serving in the German army on the Russian front in World War I. The fact that Schwarzschild derived this exact solution while calculating artillery trajectories in the trenches is one of the more remarkable episodes in the history of science. He sent the solution to Einstein in a letter. Einstein presented it to the Prussian Academy of Sciences on January 13, 1916. The solution described the first black hole, though the term would not be coined for another half-century, and Schwarzschild did not live to see its implications unfold. The Schwarzschild solution is an elegant mathematical object. It is also, almost certainly, not what real black holes look like. Real black holes rotate. They must, because the stars and gas clouds from which they form were rotating, and angular momentum is conserved during gravitational collapse. A star spinning, even slowly, will produce a black hole spinning rapidly, because conservation of angular momentum means that as the star's radius shrinks, its rotation rate increases, just as an ice skater spins faster when they pull their arms in. A star that collapses from a radius of 1,000,000 kilometers to a radius of a few tens of kilometers increases its rotation rate by a factor of billions. Observations of X-ray emissions from accretion disks around black holes have allowed astronomers to measure the spin rates of numerous stellar mass and supermassive black holes. The technique relies on the fact that the innermost stable circular orbit, the closest distance at which matter can orbit stably before plunging in, depends on the black hole's spin. For a non-rotating black hole, this orbit is at 3 Schwarzschild radii. For a maximally rotating black hole, it can be as close as the event horizon itself. By measuring the spectrum of X-rays emitted by the accretion disk and identifying features that correspond to the innermost orbit, astronomers can infer the spin. The results are striking. Many black holes are spinning at more than 90% of the maximum possible rate. Some appear to be spinning at more than 99% of the theoretical limit. GRS 1915 plus 105, a stellar mass black hole about 36,000 light-years from Earth in the constellation Aquila, has a measured spin parameter of at least 0.98, meaning it is rotating at 98% of the maximum rate allowed by general relativity. The supermassive black hole in the galaxy NGC 1365, roughly 56 million light-years away, has a measured spin parameter of at least 0.97. These are objects rotating at almost the speed of light at their equators, not solid objects with surfaces, but spinning regions of space-time itself, dragging the fabric of the universe around with them as they turn. A rotating black hole is described not by the Schwarzschild solution, but by the Kerr solution, derived by New Zealand mathematician Roy Kerr in 1963. Kerr was working at the University of Texas at Austin, and he found his solution using a mathematical technique involving a special choice of coordinates adapted to the symmetry of a rotating space-time. The discovery was not immediately recognized for its significance. When Kerr presented his result at a conference, the audience, many of them established relativists, paid little attention. It was only later, as physicists began to explore the rich structure of the Kerr space-time, that the solution was recognized as one of the most important exact solutions in all of general relativity. The Kerr metric describes a space-time geometry that is far richer and stranger than the Schwarzschild case. Several features make it profoundly different. First, a Kerr black hole does not have a single event horizon. It has two. The outer event horizon is similar to the Schwarzschild horizon. It is the boundary of no return, the surface from which light cannot escape. But inside the outer horizon lies a second horizon, the inner event horizon, also called the Cauchy horizon. The Cauchy horizon is named after Augustin Louis Cauchy, the 19th century mathematician who formalized the concept of initial value problems in differential equations. The Cauchy horizon marks the boundary beyond which the initial conditions at the outer horizon no longer uniquely determine the future evolution of space-time. Inside the Cauchy horizon, the deterministic structure of general relativity breaks down. Multiple possible futures become mathematically consistent with the same initial conditions. Between the two horizons, the space-time geometry is dynamic and complex. The radial coordinate becomes time-like, as in the Schwarzschild interior, and you are carried inexorably inward. But at the inner horizon, something remarkable happens. The radial coordinate becomes space-like again. You regain the ability to move toward or away from the center. The singularity is no longer an inescapable moment in your future. It becomes, once again, a place in space that you can, in principle, avoid. Second, the region between the outer event horizon and a larger boundary called the ergosphere exhibits a phenomenon called frame dragging. The rotation of the black hole literally drags space-time around with it, the way a spinning ball bearing embedded in honey would drag the surrounding honey into rotation. Inside the ergosphere, this frame dragging is so extreme that it is impossible to remain stationary. Even if you fired rockets at full thrust in the direction opposite to the black hole's rotation, you would still be carried along by the rotating space-time. Space itself is moving, and you are embedded in it. The ergosphere has a remarkable property discovered by Roger Penrose in 1969. Because certain orbits inside the ergosphere have negative energy as measured from infinity, it is possible to extract rotational energy from a spinning black hole. The Penrose process works like this. Send an object into the ergosphere along a carefully chosen trajectory. At the right moment, the object splits in two. One piece falls through the event horizon on a negative energy orbit, reducing the black hole's angular momentum and mass. The other piece is flung outward with more energy than the original object carried in. The black hole has given up some of its rotational energy, and that energy has been transferred to the escaping fragment. Roger Blandford and Roman Znayak showed in 1977 that a similar process, mediated by magnetic fields threading the ergosphere, could extract enormous amounts of energy from spinning, supermassive black holes. The Blandford-Znayak process is now believed to power relativistic jets, collimated beams of plasma, ejected at nearly the speed of light from the poles of active galactic nuclei. These jets can extend for hundreds of thousands of light years, far beyond the host galaxy itself, and they carry more energy than entire galaxies produce in starlight. The engine driving them is the rotational energy of a spinning, supermassive black hole extracted through the twisted magnetic fields of the ergosphere. Third, and most dramatically, the singularity inside a Kerr black hole is different from the Schwarzschild case. In a Schwarzschild black hole, The singularity is a point, a zero-dimensional object of infinite density occurring at a single moment in time. In a Kerr black hole, the singularity is a ring, a one-dimensional closed loop in the equatorial plane of the rotation. This is the ring singularity, and its geometry creates possibilities that verge on science fiction. According to the mathematics of the Kerr solution, it is possible to approach the ring singularity and pass through its center, to thread through the middle of the ring like a thread through a needle, and emerge on the other side. On the other side lies a region of space-time that the mathematics describes as a different universe. Not a different part of our universe, not a distant galaxy or a parallel dimension in the science fiction sense, but a genuinely separate space-time with its own geometry, its own physics, connected to ours only through the interior of the rotating black hole. Even more extraordinarily, the mathematics of the maximally extended Kerr space-time, the complete solution, pushed to its logical limits, describes an infinite chain of universes. You could fall into a Kerr black hole, pass through the outer horizon, survive through the inner horizon, thread the ring singularity, emerge into a new universe, find another Kerr black hole, fall in, and repeat. Each passage takes you to a new universe. The chain is infinite. The mathematics places no limit on the number of transits. Before you begin planning your interdimensional vacation, there are severe caveats that almost certainly prevent this from being physically realizable. The maximally extended Kerr space-time is a mathematical idealization. It describes a black hole that has been rotating since the infinite past and will rotate until the infinite future, with nothing ever falling in or out. Real black holes form from the collapse of real matter at a specific time, and they continuously absorb radiation and gas from their surroundings. The interior geometry of a real rotating black hole is expected to be dramatically different from the idealized Kerr solution. Most critically, the inner event horizon, the Cauchy horizon, is believed to be violently unstable. Any perturbation, even a single photon falling into the black hole after you, is infinitely blue-shifted as it approaches the inner horizon. The energy of this blue-shifted radiation grows without limit, creating a singularity at the inner horizon itself. This phenomenon, called mass inflation, was first analyzed by Eric Poisson and Werner Israel in 1990. Their calculations showed that the inner horizon transforms into a null singularity, a boundary of infinite curvature that would destroy any object attempting to pass through it to reach the hypothetical ring singularity and other universe beyond. The reality of what happens inside a rotating black hole remains one of the great open questions of gravitational physics. The idealized Kerr solution whispers of wormholes and other universes. The physics of perturbation theory shouts about instability and destruction at the inner horizon. And the unknown theory of quantum gravity might replace both pictures with something we have not yet imagined. The black hole guards its deepest secrets behind a veil of ignorance that our current physics cannot penetrate. There is one more connection between black holes and the nature of time that deserves attention before we pull back from the depths. In 1988, Kip Thorne published a paper in Physical Review Letters exploring the theoretical possibility of using wormholes for time travel. The paper was inspired by a question from his friend Carl Sagan, who was writing his science fiction novel Contact and needed a scientifically plausible mechanism for faster-than-light travel. Sagan had originally used black holes for the purpose, but Thorne pointed out that this would not work. The tidal forces would be lethal, and in any case, the Schwarzschild wormhole collapses too quickly for anything to pass through. Thorne suggested wormholes instead, and then became interested in whether they could actually exist within the framework of general relativity. The result was a landmark paper that spawned an entirely new subfield of theoretical physics, the study of closed time-like curves and the physics of time travel. Thorne showed that if a stable, traversable wormhole could be created and maintained, a significant if, as this requires exotic matter with negative energy density, which quantum mechanics permits in small amounts, but which has never been observed in the quantities needed, then it could be converted into a time machine. The method is elegant. Take one mouth of the wormhole and accelerate it to near the speed of light, then bring it back. Special relativistic time dilation ensures that less time has passed for the accelerated mouth than for the stationary one. Now step through the wormhole. You enter the stationary mouth in 2026, pass through the wormhole's throat, and exit the accelerated mouth in 2020. You have traveled 6 years into the past. Alternatively, place one mouth of the wormhole near a massive object, a neutron star, or the vicinity of a black hole, where gravitational time dilation slows the flow of time relative to the other mouth. The same temporal offset accumulates, and the wormhole becomes a gateway to the past. Stephen Hawking, upon learning of Thorne's result, proposed what he called the chronology protection conjecture, the hypothesis that the laws of physics conspire to prevent time travel from being physically realized, even when the equations of general relativity seem to permit it. Hawking's intuition was that quantum effects would accumulate near the chronological horizon, the surface in space-time where closed, time-like curves first appear, and the resulting energy density would destroy the wormhole before it could be used as a time machine. He described this as making the world safe for historians. The conjecture remains unproven. It is an educated guess, motivated by the philosophical and logical difficulties of time travel, the grandfather paradox, the bootstrap paradox, the fundamental tension between backward causation and the thermodynamic arrow of time, and by preliminary calculations showing that quantum vacuum fluctuations diverge near chronological horizons. But no rigorous proof exists. The question of whether the laws of physics permit time travel remains open. The connection to black holes is this. Black holes are the most extreme gravitational environments in the universe, and gravity is the mechanism by which time dilation, the essential ingredient for time travel, is produced. The event horizon of a black hole is, in a sense, the closest thing the universe has to a time barrier. Not a barrier that prevents time travel, but a barrier that reveals the malleability of time itself. Near a black hole, time slows, stretches, nearly stops. Inside a rotating black hole, if the idealized Kerr geometry is even approximately correct, space-time is twisted into configurations that include closed time-like curves. Whether these curves are physically realizable or are artifacts of the mathematical idealization is unknown. The black hole sits at the intersection of nearly every frontier question in theoretical physics. Can space-time be torn? Can time loops exist? Can information be destroyed? Can singularities be resolved? Can gravity be quantized? Can the universe have more than 4 dimensions? These questions are not academic curiosities. They are the bleeding edge of our understanding of reality, and the black hole, patient, dark, and silent, is the natural laboratory where the answers, if they exist, will be found. Let us now step back entirely from the theorist's blackboard and consider black holes not as mathematical objects, but as astrophysical ones. Real things, in real galaxies doing real work in the real universe. Black holes are not rare. They are not exotic anomalies scattered here and there in an otherwise orderly cosmos. They are fundamental components of the universe's architecture as essential to the cosmic ecosystem as stars, galaxies, and the vast filaments of dark matter that connect them. Every large galaxy in the observable universe appears to harbor a supermassive black hole at its center. This is not a tentative suggestion or a theoretical prediction awaiting confirmation. It is an observational fact supported by decades of measurements across the electromagnetic spectrum. The Milky Way has Sagittarius A star at 4 million solar masses. The Andromeda Galaxy, our nearest large neighbor at 2.5 million light-years, has a central black hole estimated at 110 to 230 million solar masses, roughly 30 to 60 times more massive than ours. The giant elliptical galaxy M87, located 55 million light-years away in the Virgo cluster, has a central black hole of approximately 6.5 billion solar masses, a mass so large that the event horizon is larger than our entire solar system. The relationship between supermassive black holes and their host galaxies is one of the most surprising discoveries in modern astronomy. The mass of the central black hole is tightly correlated with the mass and velocity dispersion of the galaxy's central bulge of stars. This correlation, known as the M-sigma relation, was established independently by Carl Gebhardt and colleagues, and by Laura Ferraris and David Merritt around the year 2000. The correlation is remarkably tight. The black hole mass can be predicted from the stellar velocity dispersion with an accuracy of a factor of 2 or so. This is extraordinary because the black hole, despite its enormous mass, is tiny compared to the galaxy. The black hole contains roughly 0.1 to 0.5% of the mass of the central bulge. It is like finding that the weight of a baby can reliably predict the weight of a fully loaded commercial aircraft. The implication is that the growth of the central black hole and the growth of the galaxy are linked, co-evolutionary processes that regulate each other through feedback mechanisms. When the black hole is actively accreting matter, it produces enormous amounts of energy. Not just radiation, but powerful jets and winds that can heat, push, and even expel gas from the galaxy. This feedback can suppress star formation, throttling the galaxy's growth. When the gas supply is exhausted, the black hole quiets, the galaxy cools, gas accumulates again, and the cycle restarts. The black hole and the galaxy engage in a cosmic dance of growth and regulation that plays out over billions of years. Observations with the Chandra X-ray Observatory, the Hubble Space Telescope, and more recently the James Webb Space Telescope have revealed that supermassive black holes were present astonishingly early in the universe's history. JWST has detected actively accreting black holes in galaxies that existed less than 500 million years after the Big Bang, when the universe was less than 4% of its current age. Some of these early black holes have masses of hundreds of millions of solar masses. This is deeply puzzling. If a supermassive black hole must grow from a stellar mass seed, a black hole of perhaps 10 to 100 solar masses formed from the collapse of an early massive star, then it must accrete matter at enormous rates for hundreds of millions of years to reach the observed masses. But there is a maximum rate at which a black hole can accrete matter, called the Eddington limit, set by the balance between the inward pull of gravity and the outward push of radiation pressure from the superheated, infalling gas. At the Eddington rate, a black hole roughly doubles its mass every 45 million years. Starting from a 100 solar mass seed, reaching a billion solar masses would require roughly 800 million years, longer than the time available in the early universe. Several solutions have been proposed. One is that the seed black holes were much more massive than stellar remnants, perhaps 10,000 to 100,000 solar masses formed by the direct collapse of enormous primordial gas clouds without an intermediate star phase. These direct collapse black holes would have a head start, requiring fewer doublings to reach supermassive scales. Another possibility is that early black holes accreted matter at rates exceeding the Eddington limit through super-Eddington accretion, a process that is theoretically possible if the infouling matter is arranged in geometries that allow radiation to escape without opposing the inflow. A third possibility is that black hole mergers, the coalescence of multiple large black holes, contributed significantly to early growth. The truth may involve all three mechanisms, and the James Webb Space Telescope is providing data that will constrain these models more tightly than ever before. Stellar mass black holes are even more numerous than their supermassive cousins. The Milky Way alone is estimated to contain between 100 million and 1 billion stellar mass black holes, each the remnant of a massive star that exhausted its nuclear fuel, collapsed, and left behind a core too dense for any known force to support against gravitational implosion. Most of these are dark and silent, drifting through the galaxy like invisible monuments to dead stars, detectable only by their gravitational influence on nearby objects. Occasionally, one passes through a dense cloud of interstellar gas, or finds itself in a binary system with a companion star, and the gas spiraling into the black hole forms an accretion disk that glows in X-rays, briefly revealing the invisible object. More dramatically, when two black holes orbit each other and eventually merge, they produce gravitational waves, ripples in the fabric of space-time itself, that propagate outward at the speed of light. These waves were predicted by Einstein in 1916, just months after publishing General Relativity, but he doubted they were real physical phenomena. He changed his mind several times over the following decades. The waves are extraordinarily weak. A pair of merging stellar mass black holes a billion light years away produces a gravitational wave that by the time it reaches Earth stretches and compresses the distance between 2 points separated by 1 kilometer by less than 1,000th the diameter of a proton. Detecting such a tiny signal required one of the most precise instruments ever constructed by human beings, the Laser Interferometer Gravitational Wave Observatory, LIGO. LIGO consists of two L-shaped interferometers, one in Hanford, Washington, and one in Livingston, Louisiana, separated by roughly 3,000 kilometers. Each interferometer has two arms, each 4 kilometers long, containing laser beams bouncing back and forth between mirrors 400 times before being recombined. A gravitational wave passing through the detector stretches one arm and compresses the other, creating a minute difference in the travel time of the laser light in the two arms. This difference appears as a shift in the interference pattern when the beams are recombined. The precision required is staggering. LIGO can detect changes in arm length of 10 to the negative 19 meters, 1/10,000th the diameter of a proton. To achieve this, the mirrors must be isolated from every conceivable source of vibration: seismic activity, passing trucks, ocean waves crashing on distant shores, even the thermal vibration of the mirror atoms themselves. The mirrors hang from quadruple pendulum suspensions inside vacuum chambers. The laser light is filtered, stabilized, and amplified to 750 kilowatts of circulating power. The facility operates at the edge of what is physically possible. The first direct detection of gravitational waves was made on September 14, 2015, and announced on February 11, 2016. The signal, designated GW1-50914, arrived at the Livingston detector 7 milliseconds before reaching Hanford, consistent with a wave traveling at the speed of light from the southern sky. The waveform matched the prediction of general relativity for the merger of two black holes with exquisite precision. One black hole had a mass of approximately 36 solar masses, the other approximately 29 solar masses. They had been orbiting each other for millions of years, gradually spiraling closer as gravitational wave emission carried away their orbital energy. In the final fraction of a second, they merged. The two event horizons touched, deformed, and coalesced into a single, larger event horizon. The merged black hole had a mass of approximately 62 solar masses. Notice the arithmetic. 36 plus 29 equals 65, not 62. 3 solar masses are missing. Those 3 solar masses, the mass of 3 entire suns, were converted entirely into gravitational wave energy in a fraction of a second. Using Einstein's E equals mc squared, 3 solar masses corresponds to roughly 5.4 times 10 to the 47th power joules. For comparison, the sun's total luminosity is about 3.8 times 10 to the 26th power watts. The gravitational wave energy released in the final moments of this merger exceeded the combined luminosity of all the stars in the observable universe. For a brief instant, a fraction of a second, this pair of colliding black holes in a galaxy 1.3 billion light-years away was the most powerful event occurring anywhere in the cosmos. The signal had traveled for 1.3 billion years to reach us. It left its source when multicellular life on Earth was just beginning to diversify, long before the first animals appeared, long before the Cambrian explosion, long before anything with a brain existed on this planet. By the time it arrived, that signal had weakened to a whisper, a change in distance smaller than the nucleus of an atom. And we detected it. We built a machine sensitive enough to hear that whisper, and we used it to confirm a prediction Einstein made a century earlier. LIGO has since detected dozens of black hole mergers, and it has been joined by the Virgo detector in Italy and the Kagra detector in Japan. Each detection adds data, constraints, and occasionally surprises. Some of the merging black holes have masses that fall in a range, roughly 50 to 120 solar masses, that was not expected to be populated by conventional stellar evolution. Stars in this mass range are predicted to be destroyed entirely by pair instability supernovae, which should blow the star apart without leaving any remnant. The existence of black holes in this mass gap suggests that our understanding of stellar death is incomplete, or that these black holes are the products of earlier mergers, second-generation black holes formed from the coalescence of smaller predecessors, or that they formed through exotic channels not yet fully explored. The gravitational wave era has opened a new window on the universe. For the first time, we can observe the universe not through light, not through photons, but through the vibrations of space-time itself. It is as though humanity, having studied the universe by sight for centuries, has suddenly gained the ability to hear. The Event Horizon Telescope, the extraordinary global network of radio dishes that produced humanity's first image of a black hole's shadow, represents another kind of triumph, and it deserves a closer look. The challenge was formidable. A black hole, even a supermassive one, is tiny compared to its distance from Earth. The shadow of M87's central black hole, at a distance of 55 million light-years, subtends an angle on the sky of approximately 42 microarc seconds. To put this in perspective, this is the angle subtended by a single human blood cell held at arm's length. It is the angle subtended by a coin on the surface of the moon as seen from Earth. Resolving an object this small at radio wavelengths requires a telescope with an angular resolution corresponding to an observing wavelength of about 1.3 millimeters and an effective aperture the size of the Earth. No single telescope has an aperture the size of the Earth, but a technique called very long baseline interferometry, or VLBI, can simulate such an aperture by linking multiple telescopes separated by thousands of kilometers. The principle is this: two telescopes observing the same source simultaneously record the incoming radio waves, each stamped with precise timing information from an atomic clock. When the recordings are later combined, correlated, the result is equivalent to a single observation from a telescope whose aperture equals the distance between the two stations. The resolution is determined not by the size of any individual dish, but by the maximum separation between the stations. The Event Horizon Telescope used 8 observatories on 4 continents and 1 island chain, creating an Earth-sized virtual telescope. The participating stations included the Atacama Large Millimeter Array in Chile, the IRAM 30-meter telescope in Spain, the James Clerk Maxwell Telescope in Hawaii, the Large Millimeter Telescope Alfonso Serrano in Mexico, the Submillimeter Array in Hawaii, the Submillimeter Telescope in Arizona, the South Pole Telescope at the Geographic South Pole, and the Apex Telescope in Chile. The observations were conducted in April 2017 over 4 nights. Each telescope recorded data at a rate of 64 gigabits per second, so fast that the data filled hard drives at a rate of roughly 1,000 kilograms of storage media per station per night. The total raw data volume was approximately 5 petabytes, 5 million gigabytes. This was far too much to transfer over the internet. The data was shipped on physical hard drives, crate after crate of disk packs, to correlation centers at MIT Haystack Observatory in Massachusetts and the Max Planck Institute for Radio Astronomy in Bonn, Germany. The data from the South Pole Telescope could not be shipped until the end of the Antarctic winter. The station is inaccessible from February to October, so the correlation could not even begin until months after the observations. The imaging process itself was a monumental computational challenge. VLBI data is sparse. The 8 telescopes sample only a tiny fraction of the spatial frequencies that a true Earth-sized dish would capture. Reconstructing an image from this sparse data requires sophisticated algorithms that fill in the missing information, using assumptions about the image's properties, smoothness, compactness, positivity. To ensure that the final image was robust, 4 independent teams used different imaging algorithms and were kept isolated from each other until they had each produced their results. When the 4 images were compared, they all showed the same basic structure: a bright ring surrounding a dark central shadow. The agreement was the signal that the result was real. The resulting image, released on April 10, 2019, in simultaneous press conferences around the world, showed a bright, slightly asymmetric ring of emission surrounding a dark central region, the shadow of M87's supermassive black hole. The ring corresponds to photons orbiting near the photon sphere, gravitationally lensed into a bright annulus. The asymmetry, one side of the ring brighter than the other, is caused by the relativistic Doppler effect. The side of the accretion disk moving toward Earth is brightened, and the side moving away is dimmed. The dark center is the shadow, the image of the event horizon's gravitational influence on the paths of light. The measured diameter of the shadow was consistent with the prediction of general relativity for a black hole of 6.5 billion solar masses, confirming the mass estimate derived from stellar dynamics in the galaxy. It was the first direct visual evidence that event horizons exist, that the boundary predicted by general relativity is a real feature of the universe, casting a real shadow that can be observed and measured. In May 2022, the EHT collaboration released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. This observation was even more technically challenging than M87. Sagittarius A star is roughly 1,500 times less massive than M87's black hole, and the timescale on which its appearance changes, determined by the light crossing time of the event horizon, is minutes rather than weeks. The accretion flow around Sagittarius A star flickers and morphs on timescales shorter than a single night's observation. The team had to develop entirely new imaging techniques that could account for a source that was changing even as they observed it. The resulting image, once again, showed the telltale bright ring and dark shadow, consistent with a 4 million solar mass black hole. These images are not photographs in the conventional sense. They are reconstructions built from sparse interferometric data using complex algorithms, but they are grounded in real observations of real radio waves collected by real telescopes, calibrated against the predictions of general relativity, and peer-reviewed by an international collaboration of more than 300 scientists from 80 institutions in 20 countries. They represent humanity's first direct glimpse of the boundary of a black hole, the very boundary you crossed in our imagined journey. We have traveled a great distance together, from the first distorted view of lensed stars at 10,000 kilometers, through the silent freefall and the creeping tidal forces, past the imperceptible crossing of the event horizon, through the interior where space and time exchange roles, to the singularity where physics itself breaks down. We have explored Hawking radiation and the slow death of black holes. We have confronted the information paradox and the proposals that may one day resolve it. We have peered into the spinning heart of a Kerr black hole and glimpsed, through the mathematics at least, the possibility of other universes. We have heard the gravitational waves of merging black holes and seen the shadows of supermassive monsters at the centers of galaxies. Now let us consider what it all means. The existence of black holes tells us something profound about the nature of the universe we inhabit. It tells us that space-time, the arena in which all of physics plays out, the stage on which every particle dances and every force operates, is not a fixed backdrop. It is a dynamic, flexible, deformable entity that responds to the presence of mass and energy. Mass tells space-time how to curve. Space-time tells mass how to move. And when there is enough mass concentrated in a small enough region, the curvature becomes so extreme that it creates a region from which nothing can return. A place where the familiar concepts of distance, duration, and direction cease to have their everyday meanings. This is extraordinary. The same force that keeps your feet on the floor right now, that holds the moon in its orbit around the Earth, that causes rain to fall and rivers to flow downhill. This force, carried to its logical extreme, creates regions where time stops, where space folds in on itself, where the laws of physics as we know them break down into paradox and mystery. Gravity is the gentlest of the four fundamental forces of nature. It is roughly 10 to the 36th power times, weaker than electromagnetism. You can overcome the gravitational pull of the entire Earth, all 6 times 10 to the 24th power kilograms of it, simply by lifting your hand. And yet this impossibly weak force, given enough mass, enough density, enough patience, builds the most extreme objects in the cosmos. The gentlest force creates the most violent structures. There is something deeply instructive in that, a reminder that persistence and accumulation can exceed any momentary intensity, that the quiet forces shaping the universe are sometimes the most powerful. Black holes also tell us that the universe contains genuine mysteries, not mysteries of the "we haven't measured it yet" variety, solvable with better telescopes and faster computers, but deep, fundamental. We do not yet have the conceptual framework to understand mysteries, the singularity at the center, the fate of information, the unification of gravity and quantum mechanics. These are not engineering problems. They are not puzzles that can be solved by building more sensitive detectors or more powerful accelerators, though those tools will help constrain the possibilities. They are conceptual chasms, places where our existing categories of thought are insufficient, where we need not just new answers, but new kinds of answers. When Einstein published general relativity in 1915, he did not merely refine Newton's gravity by adding correction terms or extending the range of validity. He replaced the entire conceptual framework. Newton described gravity as a force acting instantaneously across empty space between masses. Einstein described gravity as the curvature of space-time itself, not a force at all, but a geometric property of the arena in which all physics takes place. The concepts were not refinements of each other. They were fundamentally different ways of understanding the same phenomena. The resolution of the black hole's deepest puzzles, the singularity, the information paradox, the nature of quantum gravity, will almost certainly require an equally radical reimagining of reality. Not just new equations, but new concepts. Not just better math, but a different understanding of what space, time, and information actually are. And consider this. You are lying here, in the dark perhaps, listening to a description of the physics of falling into a region of space-time from which nothing escapes. You are contemplating the Kerr metric, Hawking radiation, the holographic principle, and the exchange of space and time inside the event horizon. The brain doing this contemplating is a 3-pound organ made primarily of water, fat, and protein. It runs on about 20 watts of power, less than a dim light bulb. It evolved over millions of years under selection pressures that had absolutely nothing to do with understanding black holes. Your ancestors needed to find food, avoid predators, maintain social relationships, and navigate across landscapes. There was no evolutionary pressure to understand the curvature of space-time, the quantum mechanics of event horizons, or the topology of rotating black holes. And yet here you are, understanding it, imperfectly, partially, through analogy and approximation, but genuinely understanding it. The equations work, the predictions come true, the images match the mathematics. A brain that evolved to track antelope across the savannah has derived the Schwarzschild metric and used it to predict the exact size and shape of a shadow cast by an object 55 million light-years away. And been right. This is, in the estimation of many physicists and philosophers, the deepest mystery of all. Not that the universe contains black holes, but that the universe is structured in such a way that a species of evolved primates can discover that it contains black holes, can write down the equations that describe them, and can build machines that hear their collisions and see their shadows from across the cosmos. The physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. The universe is not obligated to be comprehensible. There is no logical necessity for the laws of nature to be expressible in elegant equations. There is no guarantee that a brain evolved for survival on the African plains should be capable of penetrating the deepest structures of reality. And yet it does. Not completely, not without error, not without long detours and dead ends and centuries of confusion, but genuinely, progressively, reliably. The universe yields its secrets to careful thought and patient observation. It rewards curiosity. It responds to mathematics. It is, for reasons we do not understand, knowable. Your imagined fall into a black hole was a journey along some of the pages of that knowledge. The first chapters are well understood: tidal forces, time dilation, gravitational lensing, the structure of accretion disks. These phenomena have been observed, measured, and confirmed to extraordinary precision. The middle chapters are theoretically solid, but observationally inaccessible. The interior of the event horizon, the exchange of space and time, the finite proper time before the singularity. We trust the equations because they have been so thoroughly tested outside the horizon, but we can never verify their predictions inside it. And the final chapters, the resolution of the singularity, the fate of information, the nature of quantum gravity, are blank. They are the pages that the next generation of physicists will write, or the generation after that, or perhaps a generation so far in the future that our current theories will seem as preliminary and incomplete as Ptolemaic epicycles seem to us. But here is the thing about blank pages. They are not failures. They are not evidence that science has reached its limit, or that the universe is ultimately unknowable, or that there is nothing left to discover. They are invitations. Every mystery is a doorway. Every paradox is a signal that something deeper is waiting to be found. The history of physics is the story of blank pages being filled. Not always quickly, not always smoothly, but reliably, inevitably, through the combined efforts of thousands of curious minds working across centuries. The singularity was once a blank page. Before Einstein, no one had imagined that space-time could curve, let alone that it could curve so extremely that it would create a region from which nothing could escape. Now we know that black holes are real, that they are common, and that they sit at the centers of galaxies, shaping the evolution of cosmic structures. That knowledge was once a blank page. Gravitational waves were a theoretical prediction for a century before LIGO heard the first chirp of merging black holes. That detection was, for 100 years, a blank page. The information paradox is today's blank page. The singularity is today's blank page. The theory of quantum gravity is the blankest page of all. And somewhere, right now, someone is working on filling them in. Someone is doing the mathematics, building the models, analyzing the data from JWST or LIGO or the Next Generation Event Horizon Telescope. Someone is having the insight that will change everything. The happiest thought that will do for quantum gravity what Einstein's falling man did for general relativity. You fell into a black hole tonight. You traversed the most extreme gravitational environment the universe can create. You crossed a boundary from which nothing returns. You were stretched and compressed and ultimately torn apart by the curvature of space-time. You encountered a singularity where the known laws of physics dissolve into paradox. You learned that the deepest questions in physics about information, about time, about the nature of space itself remain unanswered, waiting for a theory that does not yet exist. And then you came back. Not from the black hole. No one comes back from a black hole, but from the contemplation of it. You emerged from this journey with your curiosity perhaps a little sharper, your sense of wonder perhaps a little deeper, and your appreciation for the strangeness and beauty of the universe a little richer than it was when we began. The universe is under no obligation to make sense to you, but it does, more than it has any right to. And the places where it stops making sense, the singularities, the paradoxes, the event horizons of knowledge, are not walls, they are horizons. And horizons, by their very nature, are not endings. They are the places where something new begins, even if we cannot yet see what it is.